Percent dissociation.
That's what we do at the
This is to determine really how much H plus dissociate, right? This is where we really left off from last week, right? So H decreases as the initial concentration decreases. Percent dissociation increases as it decreases, so on. We'll look at what the weak, because this is really for weak acids. You know that strong acid is pretty much 100% dissociation, okay? Because it's going one way. This is for a weak acid. Weak acid is in equilibrium. A strong acid is not going back. Once HCl dissociates, that's it. There's so many things you have to do in order to bring HCl back, okay? So in order to calculate amount dissociate, well, percent dissociation, we need to know how much dissociated over initial concentration. And we'll see all that.
Wait, no, please don't. I have a question.
Mm-hmm.
Can you know if an acid is weak, if a thing is weak or strong if you don't have the Ka?
Unless it tells you, if it gives you a percent dissociation, or it has to give you a Ka, or it's part of the list that you know, like the top 7. Other than that, just the random acid they throw at you, you wouldn't know if it's... You're going to assume if it's not part of your strong acid list, it's weak. Okay? And if they're giving you an equilibrium problem with an acid, chances are it's a weak acid. Yeah.
You know the one we do to see like the percent that it's less than 5%.
Yeah, that's just to check to make sure that your ignoring of minus x is good.
What you do? What is it over what?
It's x, and then whatever you were supposed to subtract the x from.
So
like if it's a 10 molar or something like that, it's x that you found over 10 times 100 to find your percentage. And if you're 5% is all you need.
Wait, where are the strong ones?
We'll go over the list later because I forgot the phone. So let's say we want to calculate percent dissociation of acetic acid. You're given Ka, 1.8 times 10 to the negative 5. You're given molarity of acetic acid. How are you going to calculate how much of this thing really dissociated? What do you need to determine percent dissociation?
You have the concentration.
Of?
The initial concentration.
Not dissociated over initial.
That's the initial.
You start with 1 molar acetic acid.
So now we need
You need what?
the amount of dissociation.
How are you going to know that? Remember, this is an equilibrium chapter.
We need to
Ice.
Aha.
No.
You have to do an ice table. It won't work any other way because once you find your X, which is going to be your H plus concentration, then you can put that over 1. Okay.
How do you do an ice?
So let's look. You have your Ka, right? You have your equation right there for Ka. Ka is given to you. Wonderful. So let's look at how we're going to do this. All right, so you start with initial 1 molar, right? Right here. So your acetic acid is 1 molar. H plus is obviously 0 to start with. Acetate is 0 to begin with. You put in your equilibrium changes as you know, minus x plus x and plus x. 1 minus x and x are equilibrium concentrations. Can you ignore the 1 minus x to be just 1?
Yeah.
Can you ignore the minus x?
Yeah.
Yes, okay. So you calculate, okay, and x squared is 1.8 times 10 to the negative 5, therefore x is 4.2 times 10 to the negative 3.
Okay.
Now, you just found H plus concentration in this solution. That means that's how much H you have. How much of the acetic acid did you start with?
They said
1 molar. So how are you going to find percent dissociation?
You put that over 1.
Yep.
Which is that?
There it is. 4.2 times 10 to the negative 3, what you found H plus to be, over the initial concentration you started with, and that's only 0.42% dissociated. That's what makes it a weak acid, and that's why you can use acetic acid and vinegar.
Hey, can you go back one more slide?
Back?
Yeah, I'm kind of confusing about 4.2. Like, how'd you get that from the ice table?
So plug into Ka. Ka is what? X squared, right? Over 1 minus x.
Yeah.
Ignore the minus x.
Okay.
Ka is x squared. Ka is given to you as, I don't know, it was like 1.8 times 10 to the negative 5.
Oh, and then you square root it?
Square root.
Okay.
Yep.
Got it.
How'd you know, like, I need ice table? What gave that?
Weak acids.
Weak acids. Just
Weak
know-
acids are in equilibrium. Equilibrium requires ice table to solve.
Because if you're looking for percent dissociation, but it's a strong acid, wouldn't it be 100%?
Yep, exactly. All right. So,
Oh.
remember we talked about this as well? I think this was like the last thing we said before we called it a day. His principle to explain why percent dissociation increases as the concentration of the weak acid decreases. So, dilution shifts equilibrium to the side with greater number of particles. So, if you're taking out the acid, right, that's one compound, but number of particles as dissociated is greater number of particles. Think about really entropy. You're thinking about increasing entropy. More particles, right, greater entropy, that's where you want to shift. Okay. Now let's do a problem where we're given percent dissociation, we're moving backwards to find Ka.
Divide by 100.
What's lactic acid? What's in that?
Lactic acid is formed by
In your
lactic
muscles,
acid
no?
fermentation in your muscles. That's what causes burning of the
And
muscles.
that's what makes you sore.
Yep.
And only thing to fix that is water.
If you actually breathe right, you shouldn't have lactic acid build up in your muscles.
But that's what people still do because when they breathe, they breathe.
Okay, so how do you do this?
Okay, so
Divide by 100, first of all.
But, okay, great, divide by 100 and all that, but what would the 3.7% dissociation, once you convert that to a, 0.037, what does that mean?
That's the
how much is
concentration.
associated?
That's the amount. That's
Over
the
initial.
amount
That's a concentration of
associated.
H.
No, that's
How
in
much?
total.
Associated.
that means how
overall.
much of the lactic acid basically is associated.
Right, dissociated. Okay, so if I say x over 0.1 equals 3.7%, what is my x?
The amount actually. The
Dissociated.
amount.
What is my x?
Square root of that.
What is my x going to indicate to me? What is it going to tell me? What am I solving when I solve for x?
What
The amount of the
Associated.
lactic acid
The H plus.
The H plus.
I said that.
H plus. That's all you're solving for.
I
Okay.
said that.
Sorry, I didn't hear you.
I think it is a round of applause. So let's give it to me.
Okay, so you know Ka is H plus, and then you have your ion, the anion over the compound, right? That's your equilibrium. So let's look at the ice table, 0.1 minus x, and x, kind of the same thing over and over again. But in this case, I'm going to find x by determining what it is, because I have a 3.7% dissociation that is given to me. So since I know my initial concentration of the compound, which is the lactic acid, I know that only 3.7% dissociates. So then I know that 3.7 times 10 to the negative 3 molarity is my x. My x is my H plus. Okay?
So how did they phrase the question? They said
They gave you the percent dissociation, they gave you initial concentration, and then they wanted, what did they want? Equilibrium concentrations?
Sorry.
Okay.
Just doing one more time.
Alright.
So in a problem like this, we're looking for the H plus concentration.
Well, that's going to give you a whole bunch of stuff after that, right? Once you know your H plus, you can figure out pH, you can figure out all the other concentrations.
Tastes like raw kombucha.
Okay. So then you can calculate your initial, your final, your equilibrium concentrations. Oh, it wanted Ka. So in order to find Ka, you already know your X, you know your initial concentration. You can ignore the minus X because it's tiny enough. So then Ka becomes 1.4 times 10 to the negative 4. It's just a plugging in. Okay, so the 3.7 times 10 to the negative 3 you found from the dissociation.
Why are we able to make it like H plus and C3H5O3 the same thing?
Because they are. They're both
It's all
X's.
part of that compound.
They're a 1-to-1 ratio.
I didn't know that.
Yes, you do.
I knew that.
You've been doing that for All equilibrium
We
problems.
did the ice table. It's
like
it's
2
a
years.
1-to-1 ratio to x and
All right, now we're going to solve acid-base problems. Mm-hmm.
But these are all FAQ questions, right?
Mm-hmm.
But these are like they put a
I'm
lot.
feeling that FAQ.
Oh my.
Okay.
He's just gonna tell you right now. He's feeling it.
0.15 molar solution of a weak acid, 3% dissociated. Calculate
Wait,
Ka.
did you go back to the problem solving?
Let's solve this first.
Bless you.
Let's go. You're solving this one on your own.
Which weak acid?
Doesn't matter. It really doesn't matter at all.
Okay. I'm comfortable.
Call it HA. Does not matter.
That's 15 times 0.03.
Let's go. Solve the problem.
Can I have this?
Yeah, fine.
And these are, remember, part of FRQ. You're never going to see these as a multiple choice. That's not possible. But definitely you're going to see some kind of equilibrium problem.
0.15
in
times
FRQ.
0.03. I need my phone to be lazy.
I think I did all. You know the answer?
We'll find out in a minute.
About the same thing.
I think it's right. 1, 2.
Oh, it's
X over 0.15 is 0.03, right?
That's what I did.
Wait.
So find X first. Once you
if
find
you're going
X,
to the
then
right,
your
is it to the
equilibrium
negative or
concentration.
to the positive?
What happened?
Like scientific notation, if you're going to the right, is it negative or positive?
Going to the right?
Yeah.
Oh, negative.
This would be 0.03.
Wait, but you're supposed to look at that.
Hmm?
Doesn't have to be x squared.
Not to find the first one. X squared. You already have find X.
One more time.
You have to find X.
But aren't there 2 of them? How far off am I if I say it's 4.5 times 10 to the negative 3?
I have no idea.
I just got 0.45.
Alright, let's go, guys.
0.45
Give me some
times
answers.
0.045. You're wrong.
You're wrong.
You're wrong.
I'm right.
Give me some answers. Let's go.
0.45.
4.5 times 10 to the negative 3. Final answer.
Wait, hold on.
Deal, no deal?
That's what I
Check
got.
that's what I got.
Wait, can you
too.
say that the X is the
But-
Ka?
Why?
So how do you convert? So now you have to convert x into Ka.
Well, the X is the hydrogen.
Right.
So
And then the anion is another X. So it's X squared over 0.15 is your K.
So it's 4.5 times 10 to the negative 3 squared over 0.15.
What?
Oh! No, you're wrong.
why is it X
just said
squared
it
on
right.
top?
Wait,
Because you would
what?
have the anion and the hydrogen.
So it'd be X squared.
When are the Olympics?
Okay.
When next one?
Wait, already?
Wait, I need you to give me 3 seconds and I'll give you my
3,
final- No.
2. Ding, 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 ding.
3, 4. Alright, got it.
Okay.
Wait, hold on.
1.4
No,
times 10 to
I'm
the
right,
negative
I'm
4.
right. I'm right, give me a high five.
You right? Who's right? Who got it?
Wait, is it
I'm
4?
not there
So-
yet.
Wait, is it 4.5 times 10 to the
Let's-
negative 3 over 15?
Shh, let's look at the problem. You guys solved for X and left it there.
No, I didn't. I saw
Okay? So when you kept on
Wait,
telling me
let's
0.045 or whatever it was, okay? That was your X. Remember, Ka is X squared over 0.15. So once you find your X, you're going to plug in square and then divide by 0.15, and you should end up with 1.4 times 10 to the negative 4.
I had 1.35, but I forgot to get it.
All right. What happened? Now bases. Yes.
I had 1.35, but I forgot to get it.
Ah.
Wait,
sig figs, your
Lizzie,
friend.
what was it that we just did? What is it called? Like, if I see the question, how do I know?
It's just solving for acid equilibrium. That's all it is. Solving for Ka. Because you can solve for Ka in many different ways, right?
I like
This
this
is with a weak acid where you're given percent dissociation. All right, now we go on to bases.
If they don't give you the actual acid, you have to assume it's x squared over whatever it is. Third base.
You're gonna get a lot of 1-to-1 ratios.
Yeah.
A lot.
Super great.
Very rarely will you get anything different. Okay, so strong base, just like a strong acid, completely dissociates. So your strong bases is all your group 1 bases, which means lithium hydroxide, potassium hydroxide, sodium hydroxide, all those are extremely strong along with group 2, like the calcium hydroxide, magnesium. So they're all very strong bases. Okay? All right, so something like calcium hydroxide, it's very low, it has low solubility because when you mix it in water, it actually doesn't dissolve very well. But it is used in many different things, such as water treatment plants. Calcium oxide and sodium carbonate are added to hard water to soften it. Hard water has a lot of calcium. That's what makes it hard water. Okay. Now, let's find pH from a strong base.
Perfect. Isn't it just the OH ion?
Right, so from this you can find hydroxide. But what do you know about pH? It's not hydroxide ion concentration.
PO.
That's pOH. But once you find pOH, okay. So in order to calculate pH, first let's deal with what we have.
Wait, isn't calculating pOH the same thing as calculating pH?
You just subtract it from 14, right?
No, but I'm talking about. I know how to calculate if I have pOH. I know how to calculate pH, but
Yeah.
calculating pOH is the same process as calculating
Negative log. Yeah. Negative log of hydroxide. So
Negative log of the
hydroxide is pOH. So major species in here, sodium, right? Hydroxide and water. Autoionization of water produces hydroxide, but we already know that the pH is dominated by the strong base. So in solution, the hydroxide is 5 times 10 to the negative 2, right? And so once you have that, so what this one did, it plugged into KW and found the H ion concentration. You don't have to. You can find pOH and subtract from 14. It's going to give you the same answer.
How do we find the POH?
You just take the concentration of hydroxide, 5 times 10 to the negative 2, and get the negative log.
And then you put that into the minus the pH, right?
That's your pH, right? All right, so note that basic solutions are greater than pH of 7. Okay. So KB, just like Ka, same thing. It's really the same thing. Now you're dealing with bases, so you have a hydroxide involved. So if you had something like a compound called methylamine, which has a KB of 4.38 times 10 to the negative 4.
What is
Methylamine is an amine base. Meth is methamphetamine. That's an amphetamine base. It's, yeah. Like Sudafed.
But don't they take that and make meth out of it?
That's why it's controlled substance. When you go to buy it, there's only so many number of bottles you can buy of Sudafed, and you have to be of age. Even like Tylenol and stuff.
No,
Any of the
Sudafed's over the counter.
behind the counter in the pharmacy most of the time.
No, I bought it like 2 weeks ago when I was sick. It was on the shelf.
Is it?
Yeah, it was. I bought it. I'm not like 18.
You should know.
I did.
They should have checked it.
But they did.
They're not supposed to sell
Is it
you.
just 'cause I look
They're not.
18?
They're not selling. They're not supposed to sell you Sudafed without making sure that you're 18.
I got
Why
like
is it 18 but then do anything else has to be 29?
Who knows?
so stupid.
All right. How would you find pH?
This country's stupid.
Now you have KB, right?
Where's the B come from?
Base. Methylamine. Amines are basic. Okay. Amines and hydroxides. These are bases. So if I wanted to find the pH, well, I know that with methylamine, that's methylamine, and they'll give you the compound, plus water, and you have hydroxide, because obviously you have to have hydroxide. And hydroxide times this ion over the compound, and obviously water doesn't count here, it's a liquid. And Kb is given to you, so you can find pOH. Right? You can find hydroxide ion concentration.
They gave you the methyl.
Yeah.
Concentration.
So if you do a nice table, right, they said the methylamine is initially 1 molar.
So
And so you plug in the same way. Nothing has changed. Just because it says Kb doesn't mean anything except that you're dealing with hydroxide ion concentration. So if you want pH, you're either going to find hydrogen ion concentration from your hydroxide or find POH and subtract from 14 to get pH.
Is that not as strong the base?
Methylamine. So here you go. POH is 1.68. Okay? So because you did the same thing you've done 1,000,001 times for equilibrium, you found X, you found POH from X, just get the negative log of this number, right? And then subtract from 14. That's all it is.
If water wasn't a liquid, would it count?
Yes. But water can never count because water will never be aqueous. It does. That's not a thing. Aqueous means dissolved in water. So, you can't. All right.
Technically, it does dissolve
If
in
water
water.
is aqueous, there's something wrong with it.
That means there's something in there.
Is water wet? That's the science version.
Water.
All right. So, polyprotic acids. What is polyprotic acid? What does that mean?
Like H2.
H2 or H3. And the Ka of the first dissociation is always stronger than the second dissociation or the third one.
So do we use the Ka for the first one?
For the most part, yes. Okay? And it'll lose one proton at a time. So if we had phosphoric acid, phosphoric acid can dissociate 3 times, 1 step at a time. First, it'll lose the H, and it becomes H2PO4 minus. Then it loses another H, it becomes HPO4 minus. Then it loses a third H, and it becomes PO43 minus with an H that it dissociates. Which one is the strongest step?
That
The first one. H3PO4 becoming H plus and H2PO4 minus. Okay? So let's start with the first one, which is H plus, and right there, you're given Ka1. Okay, so that's the first step, first Ka. Okay? So you plug in the same way. You go ahead and do the ice table. You're given initial concentration of 5 molar phosphoric acid. You know how it works, 5 minus your X and all that good stuff. You plug in. Okay? You plug in and you find pH to be 0.72. Alright? Now,
What if you're wrong if you use the other steps?
you can't use the other steps because the other steps have different K. If you're going to use the second step, how are you going to use the second step without knowing what the first one dissociated? So once you find out what the H plus concentration is, right, then you know what to plug in because Ka2 is a different value than Ka1, right? And then you can plug in and solve the same way really without having to do an equilibrium table, an ice table. And then you can do this again, and you can see by the time you get to PO43 minus, look at this concentration of phosphate ion.
So small.
1.6 times 10 to the negative 19. This is where you're not really dissociating at that step. All your dissociation really happened in the first step. The rest of them are very, 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 very weak.
So would we always have to do it like till the end?
Depending on what it's asking. Here it wanted the concentration of every single one. Like it wants the concentration of HPO4 2 minus HPO, all that. Yes.
If we get concentration that's greater than 5%,
You mean the change or the mistake?
every percent association.
You would have to use quadratic equation. It is not going to happen on the EP exam. You're not going to use quadratic equation because they're not going to give you those numbers. Yeah. Okay. All right. So
Asks if someone like really hypothetically, some person, a student got this was greater than 5%, like what would be
then your answer would be something like they would have to use the quadratic equation. They cannot make the assumption that 5 minus x equals 5. Maybe they'll give you something like that, right? Just to justify or something like that. But you're never going to plug in quadratic equation into the FRQ. Okay? All right. So what we already said, the results show the second and third dissociation steps do not make an important contribution to H+. All of your H+ is coming from step 1.
Are you looking for the hydroxide ions?
There's no hydroxide here. This is an acid.
Oh, we're doing acid.
Acid. And it gets confusing. Wait until we do titration and we put them all together. All right. Sulfuric acid is diprotic. First dissociation is very strong. It's so large for the. It's so large on the first dissociation that it's not even in equilibrium. That's how strong sulfuric acid is, which is one of the strongest ones. So we're not gonna even solve that. You can look at that on your own.
Wouldn't it be a strong acid where it dissociates completely?
Yeah, strong acid completely dissociates.
So even though it's poly.
Yeah, it dissociates, but then the second step also happens.
Okay.
Yeah, a lot less. A lot less. All right, this is not gonna happen on the AP. You're not gonna do quadratic. So we're skipping.
I love when we skip. It makes me so happy.
Okay, this we already did. This stuff. Let me see what else there was.
Nap time.
Alright, so salts that produce acidic solutions. There are certain salts when you dissolve them, you're going to get H pluses. Certain salts, when you dissolve them, you're going to get basic compounds, which we'll see more of in the next chapter, which is also acid-based, but it's titration. So basically, we're going to put the acid and base together. And by the way, this is another kind of constant, Ka times Kb equals Kw. So that's going to come in handy for next chapter.
You don't have like an addition or subtraction relationship. It's
Multiplication. Yeah. Okay, and you guys can go through the sample problems on this one. I'm not going to do it for time purposes. Okay, read through the rest. Okay, when you get to Lewis acids and Lewis bases, nobody cares, take it out. So after Lewis, you're not reading any of these. Okay, these are gone. Okay, so there's no Lewis acid base on the exam anymore. They just took it out. Because Lewis is based on an electron donation and acceptance, which puts kind of everything in an acid and everything, normal things that fluoride ion can be considered an acid. It becomes very weird.